Hey guys, hello everyone. Welcome to this video of digital image processing. So in this module, we will be covering about all the introduction of the image processing algorithms and all. This subject is basically of your computer science department subject, that is computer graphics and fundamentals of image processing. So let's start with the beginning of introduction of image processing. So let's discuss about what is a digital image first. A digital image is basically a representation of a two-dimensional visual scene that has been converted into a format, and it can be processed in any digital devices. Okay, and this digital image is basically composed of many tiny elements which are nothing known as pixels. That is all about digital image. Now what is a digital image processing? Now you know what is an image. Now how will you process that image? So it is basically the use of algorithms that you use to perform certain operations on that image. So like how many operations you are using to extract certain features from an image. So this is known as digital image processing. So let's start with this module and please stay tuned till the end. So first we have the elements of a digital image. Like what are the elements present in my image? Then we have types of images. Followed by that we have the fundamental steps. How many classes will you divide the image processing? And then we have the applications. So starting with the first topic, we have the nature of image processing. This is nothing but basically the ways of acquiring an image. How will you acquire an image basically? First is reflective mode imaging. Followed by that we have emissing type imaging, and then the last, that is transmittive imaging. The reflective imaging is basically, you say, is the simplest form of imaging. That means you are using a sensor. That sensor will acquire a digital image. Okay. So what are the examples? Basically, you have your video cameras, you have your digital cameras and your scanners. So what these three will do is they will help you to capture the image. Okay, and this reflective type of imaging, what it will do is it will convert all the light energy into digital signals. That's all about reflective mode imaging. Moving on to emissive type imaging. Images that are acquired from self-luminous objects, okay, and they don't have any other external radiation source. So how will you obtain the image then? So what happens is basically the radiations is emitted directly from the sensor itself, and from that radiation you are obtaining the image. So what are the examples of this emissive type of imaging? At first we have the MRI, that is magnetic resonance imaging, and PET, that is positron emissive tomography. Followed by that, the last we have is the transmissive imaging. The transmissive imaging is nothing but the radiation source will help you to illuminate the object. Then followed by that, the absorption of radiation depends upon the nature of the material. The material what you choose, basically the absorption will depend on that particular factor. So what happens is basically the radiations can pass entirely through the object, or it can be attenuated. Some radiations might remain attenuated. So what are the examples you can see? The examples of this transmissive type of imaging is either we have a microscopic image or it's ultrasonic imaging. So this was all about how the different methods of acquiring an image. Moving forward, next we have an image processing environment. So now you got an image. Now how will you process that? What is the environment for that? So at first we have a radiation source. Now what this radiation source will do is it will have an object. This object will be get illuminated from this radiation source. Followed by that we have a sensor. Now this sensor, what it will do is, now the analog signal will help me to convert this sensor's images into digitizer. Followed by that we are feeding the data back to a digital computer. To feeding the data back into digital computer, we are using a digital signal. So that's all about an image processing environment, guys. This diagram is very important for the VTU exam. Followed by that we have is image processing fields. Now how will you apply the application of image processing in various fields? Let's see. First we have is optics, then statistics, video, digital signal processing, graphics, machine vision. So let's talk about the examples in detail. In optics, basically what happens is we use lenses, light and lighting condition and optical circuits to obtain the image. Okay. Then next we have statistics. In statistics, what you are doing is of a particular image, you are doing the extraction and analysis of the object. Using these two things, we can get the information of a particular image. Next we have is video. Video, what you are doing is basically a video is nothing but it's a collection of images which is basically indexed by time. Followed by that we have DSP. What is DSP? DSP is digital signal processing. What it will do is it is basically the visual information in two or more dimension of a particular image. Followed by that we have machine vision. Machine vision is basically your how you extract an image and obtain its physical properties, and basically all the OpenCV algorithms mainly comes under the machine vision. Followed by that we have graphics. Guys, I have already discussed in module 1 like how the computer graphics basically works. Like image processing mainly deals with the raster data or the bitmaps, whereas the computer graphics will deal only with the vector data. Okay, that's all about the image processing in fields. Like how will you apply all this information or all these applications in various fields. That's all about this topic. Moving forward, okay, next, how will you classify an image? Now you already know the image processing environment. Now point is how will you classify the various images? So basically we have various factors. We are distinguishing the classification of images based on its nature, based on its attributes, color, dimensions, data types, and domain specific. In nature, we are categorizing into natural image, synthetic image, attributes, raster, and vector. In color, we have divided into three parts. First is monochromatic. Monochromatic is further divided into binary and grayscale. Followed by that, we have a true color and we have a pseudo color. Pseudo color is basically images are those images which are beyond the human eye imagination. Followed by that, we have dimensions, which can be the 2D format or a 3D format. Data types can be either be a signed integer, unsigned integer, float, logical, or double. Then we have domain specific. In domain specific, we have this range images and we have multispectral images. Now let's look into all these things into detail. Okay, so first we have categorized the image in the form of nature. So in nature, what happens is we are dividing into further two, that is natural as well as synthetic. In natural, what is happening is the images of natural objects are obtained using the devices like cameras and scanners. So using cameras and scanners, we are obtaining the image of natural images. Followed by that, we have synthetic. Synthetic images are those images which are generated from a computer program. Next, on the basis of attributes. In attributes, we have two methods. Again, we have raster, we have vector. In raster, you can see that the pixel and the quality of the image basically depends upon the pixel only. Okay. And in vector uses geometric attributes such as lines and circles to describe the image. So what you are doing is basically raster attribute basically depends upon the pixel. That is, depending upon the pixel only you can determine the quality of the image. And in vector, what you are doing is you are using all the geometric attributes like lines and circles to describe the image. Followed by that, we have color. In color, first is grayscale. Grayscale images are basically all the monochrome images that doesn't have any color component. Okay, now how will you represent a grayscale image? A grayscale image is basically represented as 8 bits, basically in the form of 2 to the power of 8, that is 256. So what are the examples of grayscale images? Grayscale images basically consist of X-rays, CT scan, and ultrasound images. Next we have is a binary image. A binary image is basically, you can say, an image which has pixels whose value is assumed to be 0 and 1. Next, how will you obtain a binary image? So basically, a binary image is created from a grayscale image only using a threshold process. Now, what is this threshold process? Now, if the pixel value of a particular grayscale image, if you find, is greater than a particular threshold value, then the pixel value of the binary image is considered as 1 or 0. So it's very simple, guys. You are basically comparing a pixel value with the threshold value. If you find that the value is greater than the threshold value, then the pixel value of the particular binary image will be 1, or else we are considering it as 0. Next, what is a true color image? True color image is basically the combination of various color, that is the RGB combination, that is red, green and blue combination, which I've already studied in the module 1 computer graphics color components. So next, how will you represent this? It mainly uses 24 bits to represent all the characters. Okay, so what happens is, like, we have a color image. The color image can be anything, guys. Now here we are passing it to an index value. The index is basically stores all the color components. Now we are passing it to the RGB, that is the how you represent the color combination of a true color image. Followed by that, we have a DAC. DAC is digital analog converter, and this digital analog converter, what it will do is, later once you pass it to the DAC, it will help me to render the image on the screen. That was all about colors. Now followed by that, if you see the dimensions and all, dimension is quite self-explanatory, guys. 2D and 3D, like how you represent an image in a 2D format, that is, it has an X and a Y axis. In 3D, it will have X, Y, and Z axis. Okay. Then data types. Data types, like images can be also be classified based on the data types also, that is unsigned integers, signed integers, float, logical, and double. And domain specific, basically the how the image is fixed to a particular domain. It can be either a range images, where a certain range of value is given. Followed by that, we have a multispectral images. That means the pixels range in a wide value of a spectrum. Okay. Okay, so let's continue forward. Next we have is the basic relationship and the distance matrices. So how will you represent an image? An image is basically represented in a 3 cross 3 matrix, so it can be of any size of matrix. It can be represented. So basically, if you consider an analog image of size 3 cross 3 is represented in the first coordinate of a Cartesian system. So what we are doing is, basically we have suppose for example we just give it a 0, 1 and 2. 0, 1, this is the x-axis, this is the y-axis. So here you are just plotting the values. It's like 0, 0. This is f function of an image will be 0, 0, followed by that 0, 1, then 0, 2. Then in this way you continue. Okay. So f 0, 0, that is this pixel, is the bottom left corner. So basically it starts from the coordinate position 0, 0 and it ends at 2, 2. That means this is the start point and this will be my end point. Okay. And then it mainly continues. Next is we have is the x and y. What x and y is, basically x and y are the dimensions of the image. Next, in DIP, discrete form of an image is always used, which is basically represented in our fourth quadrant. The fourth quadrant, what happens is, basically it starts from an index of 0, 0, but in case of softwares like MATLAB and all, it basically starts with 1, 1. So again, we have just plotted the x-axis values and the y-axis values. We have just given the combination 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. At the same time, this is in the discrete image of the fourth quadrant. But in case of a MATLAB software, what happens is, you are starting from 1. Here you are not considering the 0th index value. So one thing you have to remember is, in case of a MATLAB software, it always mandatorily it has to start with 1. So how is the image representation happening? Image representation is basically represented as an array where each element will correspond to a pixel value. Moving forward, logical pixels. Now what is a logical pixel? Basically, logical pixel is, basically what they will do is, it is specify a location, but they don't occupy any of the physical spaces. They are represented in the Cartesian first coordinate system, where both the x and the y axis, they are positive and they start from the origin. Next, we have a physical pixels. The physical pixels are nothing but the actual dots, okay, that occupy the space when they display on the output device. They are basically tangible and they occupy a very small area. They are represented in the fourth coordinate system, where both coordinates can be either be positive or negative, and the origin may not be in the corner. So guys, please remember this main key points when it comes to define what is a logical pixel, what is a physical pixel. A logical pixel, what it will do is it will just specify you the location but will not occupy any of the physical spaces, okay? And they are basically represented in the first coordinate system, whereas in the physical pixels they'll occupy the space, and the space occupied is a very small area, and here we are representing in the fourth coordinate system. So next, what is a image topology? Image topology is basically, it's a branch of image processing only that basically deals with the properties. Like what properties? Like image neighborhood, path among which the pixels are lying, and the connected components of a pixel. So again, we have a different ways of categorizing an image topology. First, we have is a four neighborhood pixel. What is a four neighborhood pixel? A reference pixel px comma y such that it has two horizontal pixels and two vertical pixels as the neighbor. I'll explain you this. Zero x 0. Okay, so in four neighborhood pixel, what you are doing is, if this is my center pixel, my four neighborhoods will be the vertical as well as the horizontal pixels. Okay, this is all about four neighborhood pixel. So how will you define this set? What will be the combinations? The combinations will be, if I consider this as the x-axis and this as the y-axis, so it will be x plus 1 comma y. Followed by that we will have x minus 1 comma y, then x comma y plus 1, then x comma y minus 1. So basically all these four are your four neighbors. Okay, now next we have is nd of x. So nd of x is basically your diagonal pixels. So what it's happening, for example, the same thing, if I explain you this, suppose px comma y is my center pixel, followed by that we have 0 0 0 0 values. These are some of the other pixel values are present. Then this p of x comma y, its diagonal elements will be this and this, as well as this and this. So combinations will be x minus 1 y minus 1, x minus 1 y plus 1, x plus 1 y minus 1, x plus 1 y plus 1. So guys, this is all about the diagonal representation. So I just summarize again. In four neighborhood, you are just taking the up and down vertical and left and right horizontal. Followed by that we have a diagonal pixel. Diagonal, you have to just take the diagonal elements. Then next we have is 8 neighbor. In 8 neighbor is basically your union of 4 neighbors and diagonals. So if you join all these things, then you will get the 8 neighbors. 8 neighbors basically you will have your n4 of p as well as you will have of nd of x. So this expression is very important, guys. N hat of x is equal to n4 of p, which is nothing but the 4 neighborhood pixel as well as the diagonal pixels. Okay, so let's move forward. What is a connectivity? Now we already know about what is a pixel. Now what is the relationship between two or more pixel is basically defined as your pixel connectivity. For example, if I consider two pixels p and q, so two pixels p and q are said to be connected if certain conditions are satisfied. Certain conditions in the sense, for example, they have a proper pixel brightness which is specified again by a set v, or some frequency is satisfied. So some of the other conditions must satisfy in order to ensure that yes, two pixels are connected. So next we have is for connectivity. For connectivity, what's happening is if pixels p comma q both have the same values specified by a set of v, this will be given. A q is said to be a set of n4 of p, which implies that any path from p to q, this has to be a 4 connected pixel. Then what is a 8 connectivity? 8 connectivity is like p comma q is a pixel, right? So q is in a set of n8 of p, and p comma q share a grayscale image. I'll explain this, guys, with a question I have later in this video. Next we have is a mixed connectivity. Mixed connectivity, basically you can say two pixels are said to be mixed connectivity, where q pixel is in n4 of p, that is it has a 4 neighbor, whereas q is in diagonal and the intersection of the 4 neighbor and the 4 neighbors of p and the 4 neighbors of q is empty. So that means in mixed connectivity no multiple paths are present. I'll explain this with one question, guys. You will be very much clarified with this concept. So next we have is relation. What is a relation basically? A relation is basically like two pixels I have. How will I relate these pixels? So if I consider this as a grid, suppose x1 and x2 both are together and somewhere x3 is here. So you can say x1 and x2 are in connectivity, whereas x3 is ignored because it is not anywhere connected with x1 and x2. So this is about relation. Now how will you represent a relation? Reflexive. For any element in set A, if relation, that is relation A exists, then it's a reflexive. Symmetric, if you have two pixels A and B, then it also implies that B RA exists, then it is symmetric. Followed by that we have a transitive. That means if a relation A relation B and B relation C exist, then A relation C will also exist by a transitive property. This is basically very much self-explanatory, guys. Like reflexive, symmetric and transitive properties is covered in relations of an image. Next we have is distance measure. Distance measure is basically the two pixels P and Q, which is mainly measured by its Euclidean distance, D4 distance as well as D8 distance. Okay, if I consider this as an image grid or a matrix, I would say 1 1 1 1 1 1 1 1. This entire row is called P, this is called Q, and this portion is known as Z. So D of P comma Q is basically said to be definite and finite for all P and Q. If P and Q values are greater than equal to 0, these are the basically conditions. If P equal to Q, then you have to say that D of P comma Q will be equal to 0. These are the basic conditions, guys, which we have to remember for for calculating the distance of between two pixels. Next we have a Euclidean distance. These formulas are very much important for the exam point of view. If I have P comma Q as two pixels of an image, and these are and we have to find a Euclidean distance with respect to some other points. Suppose the other points are suppose x comma y are my points and s comma t is my first, this is my first point, this is my second point. So the Euclidean distance is mainly calculated by its distance formula itself, that is under the square root of x minus s whole square plus y minus t whole square, where x comma y and s comma t are my coordinates, p comma q are my pixels. Then we have a d4 distance. D4 distance is also known as the city block distance. The formula is mod of x minus s plus mod of y minus t. Then d8 distance or the chessboard distance. The d8 of p comma q is basically the maximum value of the x minus s, mod of x minus s and mod of y minus t. So that's all about in this topic, guys. I will solve one numerical question calculating the Euclidean distance d4 and d8. Please stay tuned till the end of the video. Next we have is the important image characteristics. Now you got an image. What should be a proper characteristics of an image? First is a connected set. Connected set, what it says is, for a binary image, connected set is basically the collection of all the pixels that are basically connected to each other based on certain connectivity. Connectivity can be anything. It can be four neighbor or diagonal or the mixed one. Moving forward, digital path or curve. The digital path is basically, you can say, a path which covers from pixel P to Q, that is all the sequence of points, that is P1, P2 up to Pn. These are the points of a pixel. The length of this path is the number of pixels in the sequence. For example, P x0 comma y0 is there. This is first pixel. Second pixel is xn comma yn. If both are equal, then there is a closed path. So guys, one thing you have to remember, if P comma Q, if both the points are if both are equal, then there should be a closed path. That means it's not open. Next is region. Region is basically the connected component within the image, the set of pixels grouped together based on a certain connectivity. So it's very much understandable. We have already seen in the previous connectivity parts like N4 of P and N8 of D, where connected components are basically done based on certain criteria. Next is connected component, a subset of pixels within a connected set S. There exists a path between any two pixels P and Q within the S. That means if I have two pixels P and Q, there should be a connected path and there should be a connected component so that these two pixels are present. Next is adjacent regions. Adjacent regions are like, if I consider two regions R1 and R2, they are said to be adjacent if the union of the two adjacent regions, they form a connected component. That means you have to make sure that whenever you are doing a union of two regions, you should have a connected component, and if the region is not adjacent, then it form a disjoint set. Next is boundary. Boundary is basically the contour of an image, or you can say like it's an outline or a region which has one or more neighbors outside the region. If the border pixels are within the region, it's the inner boundary. So this will discuss in the further next modules when you learn about all the edge detection algorithms and all. Next is, what is a edge? Edge basically occurs whenever there is an abrupt change in the intensity of pixels. Whenever the pixels suddenly we have a change. So normally the edge basically occurs. They can be disjoint also, or it can be joined using the edge linking algorithms. Next we have is classification of image processing operations. So based on neighborhood, we have point operation, we have a local operation, we have a global operation. Now let's learn about each of everything in detail. First we have is point operation. Point operation, what is happening is when the output value of a specific coordinate is dependent only on the input value. That means whatever output we are getting, it's all dependent upon the input value itself. Next we have is the local operation. Local operation, what you are doing is output value at a specific coordinate is dependent upon the input value. That means it is following the same as still point operation, but it will also affect the neighborhood pixel also. That means it is not only dependent upon the input value, but also in the neighborhood of that pixel. Next is global operation. A global operation is basically the output value at a specific coordinate is dependent upon the values upon the input image. That means it is completely, you can say it will depend on all the values upon the input image. Okay. Next is how will you categorize them. First is linear operation. The linear operation basically follows the principles of additivity and homogeneity. So let's discuss about the principle of additivity. You have h of, suppose this is my function a of h of a1 f1 x comma y and a2 f2 x comma y. This can be again be represented in the format as h of a1 f1 x comma y plus h of a2 f2 of x comma y. Again what you are doing is you are taking this a1 outside of this bracket, then a1 h into f1 of x comma y. Similarly this a2 also you are taking it outside, a2 h of f2 of x comma y. So next you are what happens is you are taking this h value as x and you are converting all this f of x comma y as g of x comma y. So this is basically a1 of x g1 of x comma y plus a2 of x g2 into g of x comma y. Next we have is properties of homogeneity. Properties of homogeneity, what is happening, it's like you are adding, you have a constant inside the bracket. So it's basically you are taking it outside again, then kh of f of x comma y. Again this can be represented in the form of g to g1 of x comma y. Also you can apply certain array operations. For example, if I have a f1 image in the form of a matrix a b c and d, f2 we have e f g and h, then f1 cross f2 you have to just perform you have to just perform multiplication like a into e a e, b into f b f, c into g c g, d into h h d. So guys, please don't perform any of the matrix multiplication. It's simply like you have to just multiply this with this value, one b with f, just multiply one or the other like this way. Okay. Next we have is Arithmetic operations. Arithmetic operations, you can say like all the basic operations like addition, subtraction, multiplication and division, which you can apply on a image. Okay, so it has lot of certain expressions as well as formulas which you have to remember and write those points in exam, which is very much crucial, guys. So for the first expression is g of x comma y equal to f1 of x comma y and f2 of x comma y. Now, what is this expression basically? f1 of x comma y and f2 of x comma y are my input pixel. These two are the input pixel and this will provide me this as the output pixel. Okay, so these two are basically the input and this is the output pixel. So what is basically, you should remember one of the basic rules I would suggest, important. Please remember, guys, in numericals also it's very much important. The sum should not cross the allowed range. The allowed range is always 255. If it exceeds the pixel value, it should be set to the maximum allotted value itself. So if during addition or something you are getting any of the pixel value greater than 255, make sure it is again set down to its maximum value itself. Moving forward, similarly, you can see some constant values can also be added to a single image. Now, how will you add a constant value? Like g of x comma y, this is my output pixel. f1 of x comma y is my input pixel. This k is the constant. This you applied. Now, what are my applications? Application is like, first is the double exposure. What is a double exposure? Basically, you are superimposing an image on another image to producing a resulted image, like putting one image over the another and you are superimposing them. Also, in addition, it will increase the brightness of the image. Next we have is image subtraction. In image subtraction, what you are doing is like same, g of x comma y is f1 of x comma y minus f2 of x comma y. Again same thing, f1 of x comma y, f2 of x comma y are my input images, whereas g of x comma y is my output image. So what happens is, guys, like here you have to do a modulus operation because obviously the result can't be negative. For constants, g of x comma y is equal to again modulus of f1 xy minus k, which basically image subtraction, it will help me to decrease the brightness of the image. We have studied earlier, like in the image addition will help you to increase the brightness, whereas in image subtraction it will help you to decrease the brightness of the image. So let's talk about the applications. First we have is background elimination. For example, if you have any images, for example a very good scenery or something, you want to remove the scenery from background, so it can help in background elimination, brightness reduction and change detection. Detection algorithms are present in module 5, which I'll be posting in the next video. Next we have is image multiplication. Image multiplication is basically you are multiplying all my input pixels and then you are producing the output image. Constant, again the same thing, g of x comma y is equal to f of x comma y into k. Okay, now here one thing you have to remember is the k value can be greater than 1 or less than 1. If it is greater than 1, it follows this expression, g of x comma y equal to f of x comma y into k, whereas if k value is less than 1, then g of x comma y will be a of f of x comma y plus k. Let's deal with the applications. It will help you to increase the contrast of an image. It will help to design filter mask. The filter mask is again present in the next module. Again, it will also help me to create a mask to highlight an area of interest. Okay. Next we have is image reduction. Image reduction is like g of x comma y equal to f1 of x comma y divided by f2 of x comma y. Now what happens is once you perform division operation, it can also result in some floating point numbers also. Okay, so in case of floating point numbers, we have to round off it to the nearest integer. For constants, again the same thing, g of x comma y equal to f of x comma y divided by k. Then applications, change detection, separation of luminescence and reflectance components and contrast reduction. Okay, so let's move forward. Next we have is the application of the arithmetic operations. We performed all the addition, subtraction, multiplication and division. Now let's see what are the applications first. Now, image averaging process is basically used to remove the noise. So what is noise? Basically noise is the fluctuations of pixels values which basically occurs in an image. Okay, and as a result the quality of the image also gets affected. So what is the expression for determining the noise of an image, this g of x comma y, which is the output image, equal to f of x comma y plus eta of x comma y. This eta is nothing but the noise itself. So several instances of noise images can be averaged as g bar of x comma y equal to 1 by m of summation of I equal to 1 to m gi of x comma y, where m is nothing but the number of noisy images. Now what happens is basically if the m value is keep on increasing, then the average process, it will reduce the intensity of the noise, and as a result it becomes so low, it will get removed. Now as m becomes large, e of g bar of x comma y equal to f of x comma y. So guys, you have to remember these two expressions if the questions ask on explain the arithmetic operations of image processing. So next we have is the logical operations. Okay, logical. Okay, so let's talk about the logical operations. Logical operations are including all the AND, NAND, OR and NOR, XOR and XNOR, and the invert logical NOT operations. So what you are doing is you are taking all the truth table combinations, that is 0, 0, 0, 1, 1, 0 and 1, 1. For the C column, we take the AND operation, and for this column, we take the NAND operation. Okay, so 0 and 0, if you perform an AND operation, it will be 0. 0 and 1 is 0. 1 and 0 is 0. 1 and 1 is 1. At the same time, this NAND operation will be the negation of all these values. So 0 becomes 1 and 1 becomes 0. Okay, so the operators like AND and NAND, what it will do is it will take two images as an input and will produce one output image, which is the output of the logical AND and NAND operations. Okay, so the applications are computation of intersection of images, then you have design of filter mask and slicing of grayscale images. Moving forward, so guys, here we have a diagram. For example, if we consider the A and B are the input images, so if we perform an OR operation on this, suppose A OR operation of B, then the image becomes it takes the resembles this structure, where this is the white portion, this is the black portions. Therefore, when we perform an AND operation, this structure is basically formed. Followed by that, we have OR and NOR. OR and NOR, we just draw the truth table 0, 0, 0, 1, 1, 0 and 1, 1. 0, 0 is 0, 0, 1 is 1, 1, 0 is 1, 1 and 1 is 1. At the same time, if you take the negation of this, the 0 becomes 1 and rest all 1s will become 0. Then we have applications. Application, how it is used. OR operation is basically used for union of two images, and then OR can also be used as a merging operator also. Next we have is OR and NOR operation, XOR and XNOR and NOR. So what is the truth table? 0, 0, 0, 1, 1, 0, 1, 1 combination. 0, 0 becomes 0, 1, 1 is 0. For any combination having 1, at least one value, then it will be 1 and 1. Others similarly for XNOR, just take the negation value itself. So what is the application of this? It is basically help in change detection. Also, it is used as a sub-component of a complex image processing operation. So the diagram of the result XOR operation is somewhat like this. If we considering the same this only as an input image A and B, if we perform an XOR or NOR operation, you will get this kind of figure. Okay, moving forward, invert logical NOT. So basically whatever input, that is 0 or 1 you are providing, the output will be the negation of it. So for grayscale operation, it is mainly given by g of x comma y 255 minus of f of x comma y. Next we have the applications. Applications basically are the obtaining a negative of an image, also making features which are clearer to the observer. Also it helps in morphological processing. For example, if we consider this as the image, this is the white portion, this is the black and white portion. If we perform an invert operation, then the entire image gets black. Next, we have seen about all the logical operations, arithmetic operation. Next we have is the geometric operations. Geometric operations, like if we recall what we have studied in the OpenGL concepts, we had translation, rotation and scaling. So here also the same thing we are doing, translation. So what is translation? Basically your movement of an image from a particular old coordinate to a new coordinate position. Okay, so x dash, suppose let us assume my x and y are my initial coordinates, then x dash and y dash are the coordinates where we want to push the image. So x dash will be equal to x plus delta x, y dash will be equal to y plus delta y. This can again be represented in a vector representation. F dash is equal to f plus t. So how will you represent this? The main equation is very much important, guys. X dash, y dash and 1, this is the new coordinate, how will be represented by this matrix format: 1 0 delta x, 0 1 delta y, 0 0 1. This 0 0 1 is nothing but the homogeneous parameter into x y 1 into transpose. Okay, next we have a scaling. Scaling is basically you are trying to enlarge an image or you want to shrink an image. So what is the formula for this? X dash is equal to x into x of sx, y dash is equal to y into sy. This can be again represented in the form of x dash y dash will be equal to sx sy 0 and 0 x comma y. Moving forward, so the previous example what we have seen of Sx and Sy, it was of 2D. Now if I consider a particular 3D part, then if we consider a homogeneous parameter as well, then x dash y dash 1 will be equal to Sx 0 0 0 Sy and 0 0 0 1 into xy comma 1 of whole transpose. Then followed by scaling we have is reflection operation. Reflection operation is basically where you obtain the image but the pixels are reversed. So we have reflection around various axes. First we have is reflection around the x-axis. So guys, there is a trick to remember this. Please listen it very carefully. Suppose f dash is the particular pixel of the output image I want. So if I have reflection around x-axis, f of x comma y, just remember this, guys. Okay, so whenever the question says the reflection is around the x-axis, make sure whenever it is in x-axis, this representation value will have minus here, and here it will be normal plus. Okay, now when you're representing the same in the matrix format of zeros and ones, this will be 1 0 0 and minus 1. That is, this one is my x value, this one is the y value into xy transpose. At the same time, the same goes for reflection along the y-axis. Along y-axis, how it occurs is, like if it is says along the y-axis, just take here as f equal to x of x comma minus y. This can be again represented in the matrix format as, here it will x value will be minus, here the y value will be minus. At the same time, for x-axis, here the x value will be minus, and here it will be, for y value it will be minus 1 into xy transpose. Reflection about y equal to x, whenever it is says y equal to x, just remember one thing, you have to just, this 1 and 1 will, this diagonal element will shift to here, so it will be 0 1 1 and 0 into xy transpose. Next we have reflection about y equal to minus x, so it is represented as f minus f dash equal to x comma minus y equal to 0 0. This will be minus 1 into xy transpose. So guys, you have to remember all this matrix representation because this will be very helpful for you whenever you are solving the numericals. Okay, next for homogeneous coordinate system, remember for y-axis it is, as I always know, for y-axis that means x is 0. So for the x coordinate, just put minus 1. So it will be minus 1 0 0 0 1 0 0 0 1 will be the homogeneous parameter. At the same time, x-axis will be y equal to 0. So just put 1 0 0 0 minus 1 0 0 0 1. R equal to origin, whenever it is origin, just put minus 1 in all these diagonal elements, rest all will be 0. This is your homogeneous parameter. Next, r equal to y equal to minus 6. For example, this is my coordinate system, the reflection is somewhere occurring around like this. Okay, you know, I guess y equal, this is y axis, this is the x axis. If the reflection is occurring through y equal to x, then this matrix is the way of representation: 0 1 0 1 0. Just one shortcut you have to remember, like for y axis and x axis you had minus 1 and 1 here. Now in reflection around y equal to x, just have to reverse the diagonal elements. So this will be 0 0, this will be 1 and 1. Similarly for y equal to minus x, just put the negation symbol. Next, what is shearing? Shearing, basically what it will do is a transformation only that produces a distortion in the shape. Now distortion in the shape can occur in both x direction as well as in the y direction. So let's look at the expressions. So x shear will be denoted as x dash equal to x plus ay, y dash equal to y. So one thing you have to remember is for x shear it says x shear will be y will stay as it is, only the x value will change, that is x dash will be equal to x plus ay, y dash will be equal to y. So x shear will be this representation format 1a0 0 1 0 0 0 1. Make sure this all diagonal elements is having 1 1 1. Then y share will be equal to, now here it comes about y share, your x will remain as it is, y dash equal to y plus bx. So it will be 1 0 0 b 1 0 0 0 1. So this is this a is nothing but your shx and this b is nothing but your shy. Okay. Next we have is rotation. Rotation is like how will you rotate an image by a particular angle. For example, x dash y dash are my new coordinates. This is my coordinate representation cos theta, then minus of sin theta and sin theta into xy transpose. So again this can be represented in the vector format, f dash equal to r into a. R is the rotation matrix and a is the current coordinate, which is where the image is present. Now the angle mainly depends upon whether it's clockwise or anti-clockwise. For a positive angle it is in a clockwise rotation, whereas in a negative angle it's an anti-clockwise rotation. Next we have is an affine transform. Affine transform is basically a transformation only that will map a particular pixel value, for example x comma y, to a new coordinate position, and then you get a transformation equation. So x dash equal to tx of x comma y, y dash equal to ty of x comma y. This is the way of representation, whereas tx and ty are nothing but a polynomial equation, and here it can be represented as, for x dash you can say equal to a naught x plus a1 y plus a2, y dash equal to b naught x plus b1 y plus b2. Again, if you want to represent it in a matrix format, it becomes x dash y dash 1 equal to a naught a1, just take the coefficient a naught a1 a2 b naught b1 b2. Next last one is the homogeneous parameter x y and 1. Moving forward, so guys, there are a lot of operations, you can say geometric operations, a lot of matrices are there in the question. If they ask about explain all the different types of geometric operation, you have to write all these equations. I'll put a video on all the important questions on image processing, so please stay tuned till the end. Inverse of transformation. Inverse transformation, what it does is it will restore the transformed object to its original form. Okay, like different transformations you're performing. For example, in the earlier you have seen I have performed translation, rotation, scaling. That means you are in translation, what you are doing is you are shifting a particular image from one coordinate to another coordinate. But what if I want to shift the image back from final to the initial? So it was very simple. Whatever the matrix equation we have seen before, that is delta x and delta y was present here, just put a negation symbol. This negation symbol is nothing but you are going to transform the image back to your initial position. Similarly, for inverse rotation, we had cos theta sin theta 0 minus sin theta cos theta. Here we had a minus symbol, just you have to change the minus to plus. That's it. Inverse scaling also, for example, if I want to shrink an image, I want to enlarge it back, just put the negative symbol and vice versa. Next, this was all about 2D transform. Next we have a 3D transform. 3D transform is also very simple, guys. Just like for 2D we had an x and y, for 3D you will have a z value also. Same thing, translation 0 0 0 delta x, 0 0 1 0 delta y, 0 1 0 0 0 1 delta z, and 0 0 1 is the homogeneous parameter. Similarly for scaling, sx xy sz. Rotation also. Now rotation, guys, one thing you have to remember, that is rotation around x axis, y axis or z axis. Whenever it asks rotation around the x axis, keep the first row as completely as 0. Okay, no need to change anything. And similarly the last fourth row will become the homogeneous parameter. Just change here itself, that is cos theta minus sin theta and cos theta. Rest all coordinates remain 0. At the same time, r of y comma theta, that is x, that means x and that means y will be 0. So just you will put the coordinate the diagonal element as 1. Rest all will be filled with zeros. Just fill only the x and the z coordinate. That means cos theta sin theta minus sin theta cos theta. Similarly for z-axis will be the the entire z turns 0. Cos theta 0, cos theta 0, sin theta 0, 0, 1, 0, 0, minus sin theta 0, cos theta 0, 0, 0, 0, 1. At the same time, for the reflection also, just change the value of where it becomes -1 and when it becomes +1. That's all about 3D 3D transformation operation. Similarly comes for sharing also, like one more axis will be added. Now next, talk about the image interpolation techniques. Now image interpolation techniques is basically of three types. You can say nearest neighbor, bilinear and cubic. What is forward mapping now? Forward mapping is basically the process of applying transformation iteratively. You are applying it to each and every pixel and you are getting a new coordinate. And in that new coordinate, you are copying the values of pixel to a new position. Okay. Now what is a backward mapping? Backward mapping is process of checking the pixels of an output image to determine the position of a pixels in the input image in order to guarantee that all the pixels of the image are processed. So what is happening is backward mapping. Backward mapping, like once you get the output image, you are determining the position of the input image as well, and you are checking whether all the pixels were processed properly or not. So sometimes it may happen like some of the pixels are not fitted in the new coordinates. So let's understand this with a very pretty good example. Suppose x dash equal this formula I have taken for this rotation equation, that is x dash equal to x cos theta minus y sin theta, where my point is given is 10,5 and theta is 45 degree. Okay. Similarly, for this we calculate all the coordinates of x dash and y dash. You get x dash as 10 cos 45 minus 5 sin 45 degree. You calculate it, you get 3.535. At the same time, y dash equal to x sin theta plus y cos theta, you get 10.065. Now one thing I would say, here we are getting a decimal point values, but in decimal point values that is not quite possible when you are trying to represent this image. So you have to round it off to the nearest integer. So 3.535 will be represented as 4, 10.605 will be represented as 11. So the new coordinate will be 4, 11. Moving forward, now you have already seen the image interpolation has three ways of representation. First we have is the nearest neighbor. Nearest neighbor, what it does is it determines the closest pixel and assigns it to every pixel in the new image matrix. That means the brightness of the pixel, like brightness of each and every pixel, is equal to the all the closest neighbors. Okay. But sometimes what happens is it may occur a pixel blocking, and then this pixel blocking, what it will do is it will distort the resulting image. As a result, it will result in aliasing. So aliasing is basically when there is sometimes a pixel blocking and the what particular image I want to get, it gets distorted. The shape is not proper. So that is called aliasing. Next we have a bilinear technique. Bilinear technique is the first order of interpolation. What is happening is the four neighbors of the transformed original pixel that surrounds the new pixel are obtained and are used to calculate the new pixel value. Guys, this is much more similar to the four neighbor connectivity and 8 neighbors connectivity. Like g of x comma y is my output image. So if I consider a pixel value 1 minus a 1 minus b f of x comma y plus 1 minus a of b f of x dash of y plus 1 plus a of a minus a of 1 minus b into f of x dash plus 1 comma y plus ab of x of x plus 1 and y dash plus 1. So if the desired pixel is very close to one of the neighbors, its weight will be higher and it will result in blurring of an image. So basically it says that if while performing this calculation, if you find the weight is too much higher with the neighboring pixels, then sometimes what happens is it will result in the blurring of the image, which is again similar to aliasing only. Okay. Next we have is bicubic technique. Bicubic technique is the second order of interpolation. So what is happening is its neighborhood has 16 pixels. Here the neighborhood was having only four neighbors. Here we had 16 pixels. So what it will do is it fits two polynomials to the 16 pixels, the transformed original matrix and the new image pixel. Okay, it's quite theoretical, guys. It doesn't have any proper diagrammatic explanation though. So these three are the main points when it comes about describe the image interpolation techniques. Rest is set operation. Set operation is like you are given a combination of a of 0 0 0 to a of 0 0 0 2 and 2 comma 2. So what you are doing is here in the question it will be given, suppose this is my matrix. I will say 1 0 1 0 0 0 0 0 1. Okay, so as you all know, the image is basically represented in the form of matrix structure. If I number it as 0 1 and 2, 0 1 and 2, so you can say like wherever we have a 1 in this matrix, I can say there lies an image. So where can I lie an image? The sets will be 0 comma 0, 0 comma 1, sorry 0 comma 2 and 2 comma 2. That means these three combinations will represent a value of 1, which means that these three combinations can be used for image analysis. So just a basic mathematical equation is present. This A complement will be equal to C slash of epsilon naught of A. A is equal to C of minus A of A epsilon naught A, and A union B equal to C such that C belongs to A and it's a union of C belongs to B. Similarly, we have for union for intersection also and for A minus B as well. Next comes what is dilation. Dilation basically what we'll do is it will increase the boundary of a region while the small holes which are present in the image becomes smaller. So let's understand this with a very good example. This is my question where this is my image this is my image matrix 0 0 1 0 0 1 0 1 1. Here we have given the index values. So the question says like you apply the dilation and erosion to the image where S value is 1 comma 1 and the coordinates are 0 0 and 0 1. So what is my first step is, first like you have to represent this particular this matrix in the different combinations. So here it says like image F can be written as F equal to 0 comma 2 1 comma 2 2 comma 1 2 comma 2. So what you are doing is basically wherever you are having 1, just take those combinations. Fine. And S value is already given as 0 0 and 0 1 in the question itself. Now what is the algorithm for dilation? The first step is you have to add all the coordinate values of S to F. Just add the values, guys. 0 0 0 plus 0 0 0 plus 2 2. Then you can then 0 plus 1 1 2 plus 0 plus 1 1, then again 2, then 2 1 2 2 0 3 1 3 2 2 and 2 3. Just add all this all the pixel values and get this combination. Now once you get this combination, you have to eliminate all the redundant or the duplicate pairs. Okay, now you can see my values which are repeated. I can see 1 comma 2 2 comma 1 is repeated in this picture, so you have to eliminate any one among these. So next what is the process is you have to take the union of this sets. Now once you take the union of this set, it will result in dilation. So just if this is my, you can say this is the original matrix 0 0 1 0 0 1 0 0 0 1 and 0 1 1, like whatever combinations you have got, just add a 1 1 1 here. That means 0 comma 2 you have a 1, then 1 comma 2 you have a 1, then 2 comma 1 you have a 1, then 2 comma 2 there is a 1, 0 comma 3 has a 1, 1 comma 3 has a 1, and 2 comma 3 is also having a 1. This is all about dilation. The dilation, it's very easy, guys. The algorithm follows is we have to add all the coordinate of S to the value coordinates of F. Then you perform a dilation operation. You take the combinations. Once you take the combinations, you remove all the repeated pairs and then you perform the union of the sets. Once you perform the union on these sets, you get the resultant dilated image. Next is erosion. Erosion, the same algorithm follows as dilation, but what the major difference is, here you are taking the union of all these elements, but here you have to take the intersection. And here we don't remove any of the redundant values. For example, in the step 1, what you have to do is you have to subtract the coordinates of S from all coordinates of F. Like here we perform addition, here you have to perform subtraction. So F erosion S will be equal to, just subtract the pixels, guys, like 0, 2, 0, 0, 2 and 0, 0, it will be 0, 2. Then 1, 2 minus 1, 2 minus 0, 0 will be 1, 2. 2, 1 minus 2, 1 minus 0, 0 will be 2, 1. 2, 2 minus 0, 0 will be 2, 2 itself. Then again you just minus it to 0, 1. 0, 2 with minus 0, 1 will be 0, 1, followed by 1, 1, then 2, 0 and 2, 1. Here you find the intersection or the common element. You can see 2, 1 is my common element. It is repeating. So what I will do is I'll just take this as my intersection element, and in this intersection element, suppose in 2, 1, the resulted image, whatever I take, like first if I consider 0, 0, 0, only 0, 1, 2, 0, 1, 2. Make sure whenever it comes to erosion, only the intersection element, that is 2, 1, only in 2, 1 there should be a 1, rest all will be filled with zeros. That's all about erosion. Moving forward, statistical operation is quite similar, guys. You know already about what is a mean. Mean is basically you are adding all the values divided by n, median and mode, percentile, standard deviation and variance, and entropy. It's very much self-theoretical and doesn't have any much content as per in the textbook. So let's search about what is an entropy. Entropy, what you are doing is you will get a good numerical question on this. The formula you should remember, that is H is equal to minus of summation of I equal to 1 to n, P of I log 2 of P, where Pi is the prior probability. Entropy is basically, I would say, you are calculating the randomness of any of the pixel of an image. That's all about entropy, right? You are finding the randomness or disorder. Fine. So this is a particular image matrix 1, 2, 3, 4, 3, 4, 4, 6, 9, 9, 8, 7. This will be already given in the question. Now how to calculate the entropy of this image? It's very easy, guys. You have to check how many symbols are there. I can see in this particular 4 cross 4 16 boxes, I have all the numbers ranging from 1 to 9. Okay, so once you write all the symbols, then you calculate the probability of occurrence of each symbols. First is 1. Calculate in this grid how many times 1 has appeared. You can see 1 has appeared 2 times, so it will be 2 by 16. At the same time 2 has appeared 1 times, 1 by 16, followed by 3, 4, 5, 6, 7, 8, 9. Just calculate all the probability of occurrences. Then once you finish this, you have to find the entropy. Entropy will be minus of start pi is nothing but 2 by 16. 2 by 16 again log base 2 of 2 by 16 plus next 1 by 16 log 2 of 1 by 16, 3 by 16 log 2 of 3 by 16 plus 2 by 16 log base 2. Guys, please remember this has to be log of base 2, 2 by 16. At the same time, keep on adding this. Once you add this, you will get this resultant answer as 3.075. So just remember this formula, and remember you have a minus sign here also, like outside the bracket, and remember to put log of base 2 in the calculator while you are solving it. So let's move forward. Okay, so that's about module 4. So module 4, what we have covered, if I recall from the starting, we had is what is image processing, how will you categorize the images, image processing environment, its application. And followed by that, we had the neighboring pixels n4, nd, and n4 of x. Then we had all the various operations, arithmetical, geometric. Then we have dealt about all the entropy questions as well. So that's all about this module. I will be uploading the important questions of this module 4 of digital image processing. Please stay tuned. If you have any doubts, please let me know in the comment section. Until then, please like, share and subscribe. Thank you, guys.